Hello and thank you for joining this session. We will show you today how you can add intelligence to the Open RAN using dRAX RAN Intelligent Controller. We'll look at three main topics today. We'll show you a short overview of Accelleran dRAX RIC, and then we'll dive into the demo with an ANR xAPP demo and a smart handover demo. Let's start with a short dRAX overview. For demos, we'll be using dRAX, which is Accelleran's cloud-native Open RAN platform. dRAX consists of a 4G CU, a 5G CU, a near real-time RIC, which hosts xAPPs as well as some SMO layer, and all of this communicate through a high-throughput messaging bus and is a fully cloud-native platform orchestrated with Kubernetes. dRAX RIC is a fully productized developer platform which hosts xAPPs from Accelleran, but also from third-party developers who are taking advantage of this platform. For demo, we have deployed our near real-time RIC on an ARM Graviton platform on AWS, while the 5G CU, the 4G CU, and the other RAN elements are deployed at Accelleran in our lab. The near real-time RIC and the CUs belong to the same Kubernetes cluster. Let's look at our first demo, which is an automated neighbor relationship xAPP focused on 5G network, and we'll get you acquainted with the dRAX dashboard. So what we see initially is a 5G cluster of small cells where we don't see any neighbor relationship because the xAPP is not yet installed. So what we'll do next is onboard our 5G ANR xAPP. To do that, we go to the xAPPs tab and we choose to deploy the xAPP. We first enter the metadata for these xAPPs, which are basically the name, the release, and how we want to upload the xAPP. In this case, we're going to upload a local xAPP that we have on our machine. Once this is done, we can go to the xAPP tab and we see that this xAPP is now loaded and running. Now that the xAPP is running, we see directly the effect on the dashboard. We will see the neighbor relationship building up and the 5G small cells clustering as they are geographically located. So you see here building up 3 clusters. If we now add another node to the network, you will see that the algorithm will keep on building the relationship between this node and existing cluster. So that is how our ANR xAPP builds automatically neighbor relationship. Let's move now to the next demo, which is a demo of our smart handover xAPP. Let's look at our scenario, which takes place in a private cellular environment. In this case, we have an AGV which is moving from the warehouse to a production environment. The warehouse is covered by 1 small cell and the production environment is covered by 2 small cells. When it comes to the handover between the warehouse and the production, we will compare basically 2 algorithms, the standard A3 algorithm for handover to a RIC-triggered smart handover, which the smart handover xAPP will control. It is important to note that when the AGV moves into the production area, it has basically the choices between 2 small cells. One of them is already loaded by 2 fixed UEs representing, for instance, surveillance cameras. Let's first see what happens when we don't use the RIC to trigger the handover, but that we rather let the standard A3 algorithm manage the handover on its own. Let's go back to our dRAX dashboard to look at the evolution of the throughput during the movement of the AGV. The first thing we see is this moving UE, the AGV, moving from the warehouse area to the production area. We also see the 2 fixed UEs, which I described earlier, representing, for instance, surveillance camera, which are loading one of the small cells serving the production area. The orange line on the throughput graph represents the sum of the throughput of the 3 UEs which are part of our cluster. Our AGV has been entering the production area and will now hand over to one of the 2 small cells which are covering this area. The standard A3 handover algorithm only look at the RSRP to trigger the handover and will therefore trigger a handover to the strongest serving cell that is available to the UE. In our case, the AGV will attach to the small cell already loaded by 2 other UEs, and as we can see, the total throughput will be impacted by this choice. We've lost more than 10 megabits per second of aggregate throughput following this handover operation. Let's see now how things go when we use our smart handover algorithm, and you will see that things are totally different when the RIC takes over. When the smart handover xAPP takes control, it will trigger the handover differently. The AGV will hand over to the least loaded small cell, which in this case is production 1, as you can see on the picture. Basically, the RIC has triggered the handover by taking into account the congestion level of the candidate small cells for handover. So it not only looks at the signal strength, but also at the congestion level. And by doing so, it's going to optimize the aggregate throughput of our UEs which are in the cluster. So what you can see is that the throughput is being maintained before and after the handover, unlike what we've seen in the previous algorithm where the standard handover was applied. This is a very concrete case of how the RIC can bring intelligence to the RAN, and in this case, optimize the throughput and spread the load across the cluster. Thank you for joining this session, and of course, if you want to learn more, don't hesitate to reach out.